Welcome back to Biodegradable Materials. I would like to continue from last time, so let's have a quick recap. We had a chain molecule like this, and there was a reaction with oxygen. It was a special type of oxygen that generated a peroxide on the side of the chain. And then we established, although we didn't establish, we just decided it, but we're going to investigate that now. We discovered maybe that there was a radical generation reaction, which I told you was the rate determining step, is the slowest part of the reaction. Let us investigate that first. In previous chemistry courses, organic chemistry for example, our biomaterial students will be familiar with this reaction of tertiary butanol with hydrochloric acid, which is a first order reaction. What that means is that the concentration of hydrochloric acid is very low effect, even though it appears in the reaction. So we go to this thing, Cl plus H2O. So we make water, and we make this, so we're replacing this OH with a Cl. That's the reaction. But what we discover is if we change the concentration of hydrochloric acid, it doesn't really affect the reaction at all. Obviously, if there's an incredibly tiny amount in, it doesn't go. And if there's loads and loads in, it goes slightly faster. But what we really see is if we change the concentration of this reagent, the rate of the reaction changes massively. So we can see in this reaction that we've got two steps. The first step being this part of the molecule dropping off, the OH minus dropping off and forming a carbocation. This is a positive charged carbon molecule or carbon atom. And this positively charged carbon atom then reacts with the hydrochloric acid. What we measure in this reaction is that this step is very slow and this step is very fast in this particular case. And what that means is that this reagent, the hydrochloric acid, is unimportant as to the rate of the reaction. Because we're interested mostly in the rate of degradation here, rate is going to be of critical importance to us, so that's why we're talking about it. So we call this the rate determining step because it's the slowest, and it's so much slower that it means the others are irrelevant for how fast the whole reaction appears to be. So effectively, this is falling apart a little bit all the time into this carbocation, but this is super reactive, and so it searches for any negative ions, OH minus or Cl minus, and it reacts with those to form the product. Okay, I think I may have had to cut a piece out just there because I drew something wrong. So let us carry on from this side anyway, because I've changed my picture. We've got the radical, and this radical will now be able to do things. We will be able to interact with other things. What we had last time was the reaction of a single radical, of an O dot radical actually, with a double bond to form, it's a one electron process to form a new bond and to form a new radical, which can then cause radical polymerization, which is a common form of polymer growth when we want to make polymers. But here we're actually destroying them. So why is that the same thing? Well, inside a polymer solid, there is no monomer for it to react with. There are no double bonds hanging around to react with our radical here. So what we've really got next door to it is another polymer chain. And the polymer chain has not very many bonds that it can react with. So it can either react with this hydrogen on the side, or it can react with this carbon. If it reacts with the carbon, it's cutting the chain shorter. If it reacts with the hydrogen, then it is either making a cross link between the two, and so if it goes into here, which is the less likely way, making a hydrogen radical. That's not very likely, but let's draw it anyway. So we would then form this plus an H dot. So we formed a cross-link. Cross-linking is a fairly common procedure with radical polymerization, but that is going to make our polymer stronger. It is going to make it more brittle, and that's what we see if we allow a polymer to age. So if we take our polyethylene and we leave it outside in the sun, it will first of all get more brittle, and then eventually it will go all sticky. If we take an elastic band and we leave it in the drawer, all of you have probably done this by accident. If you leave an elastic band in a drawer for a few years, it first of all goes hard and crunchy, and then it goes sticky and horrible, and then it goes back hard and crunchy again effectively. So what is happening is it's cross-linking, making it stiffer, so it then isn't elastic anymore, and then it cuts the polymer chain shorter, and then it becomes a liquid. The more common reaction here would be a hydrogen abstraction. So I'm then going to put my radical in and steal an electron out of the bond. That gives me, oops, my pen is too good. But let's do it. So that gives me OH here, and it gives me radical here. And this radical can now rearrange. So now we have a new subject. This is the bit that I probably had to delete. There was a mistake, so we'll see what we can do. If we have this group, what will typically happen is this radical will try, or will tend to reduce in energy, and it can be reduced in energy by finding a more substituted bond. So what is actually happening is this radical is shared with orbitals that it can connect to. So we can see the radical is in an orbital that used to be a bonding orbital to the hydrogen, and another orbital that is connected to it would be one that's in a bonding orbital to a hydrogen over here. And the other one, possibility, is one over here. I've drawn it in a weird way, but they're one over, I can't get it to join up. One of these two, depending on which way, because it's in 3 dimensions and not 2. So if we rotate that so it's actually sticking out, it's the same as that one sticking out here. Likewise, so if it's on the top, and this one on the top will also have a certain amount of overlap with it. We can rotate them so they're actually in the same plane, and that can donate electron density or share electron density better to share the radicalness, the single electron, over more carbons. It's not a very good way of doing it, but it does do it a bit. And that reduces the energy, makes it more stable, makes it easier to form. Another thing that it can do is it can shift a methyl group. So a methyl shift is fairly typical. If we have a methyl group on a neighboring atom, so this one here, for example, we could shift, let's put a methyl group like that, so we don't have to move the whole thing. We could shift it into here. That would also move our charge along. But now we have to worry about, where does the radical end up? Because the radical should end up on the most substituted place possible. So it doesn't help if we shift our methyl group along and the radical ends up over here. So if we look into it a little bit further, we can see that it's more common in this particular reaction with the radical, because if we react to this radical with this hydrogen bond, we can take one electron from the bond and add it to the radical. So we move the hydrogen over to here, and then the radical, the other electron in the bond, will end up here. So effectively the radical will swap places with the hydrogen. What that means is that it's difficult to do a methyl shift and get an advantage. It's not quite the same with carbocations, because that works slightly differently. But here we have a new species with the radical on a more substituted position. So this is quite a common can rearrange to be more stable. And now this is going to go and attack something else. So we had the connection directly between an oxygen and another chain, but let's have another chain with a radical on it. We can also form a direct single bond between our two chains, like that. That will also make it bigger and more brittle. And now we will think about how we're going to break our chain. So I've made two new reactions. This is our chain with a radical on it, and it could break, forming a double bond here, as long as we've got something nearby that can assist, typically another molecule, typically another polymer molecule, which would allow us to remove a hydrogen off there to make a double bond on here. We'll do the same thing up here, but with an oxygen in, it's a little bit easier. So the oxygen will then take an electron to form a double bond O. Let's resolve that first so that we know what we're getting onto. So we would then have this species here, which is not radical anymore, and we've broken this bond. This would be a radical, but we will do the same thing here. We will give a hydrogen up and form a double bond instead. That is typically what would happen. It's lower in energy and it's more likely to break. It's quite hard to break these bonds, so it's more likely to break if there's something around, another polymer chain, helping the reaction to take the proton off, to take the hydrogen away. Not the proton, the radical away, it effectively removes the radical as a hydrogen dot, so that will get lost. So now we have two new species and we've broken the chain. Whoops, let's do this one as well. We've made two new species here, and that's broken the chain. We've got to do some hydrogen movement here to get this hydrogen back onto here so that we're back to happy. So we can break our chains as well as make them in the same way that a Diels-Alder reaction goes forwards and backwards. So let's have a quick look at that too. So this will be a simple Diels-Alder reaction where we kick electrons around in a circle. This would be a 6-electron Diels-Alder process, and we would form a new molecule out of that that would go to this cyclohexene. And cyclohexene can break down in high energy environments with the reverse Diels-Alder reaction, which is just a cyclic movement of electrons, which is the same as we had with our oxygen reacting with the bond to start with. It's also a similar type of reaction. It comes from the same family, where effectively we've got a temporary intermediate step, or the intermediary goes via something that looks a little bit like a cyclic molecule, like a benzene, or another number of bonds, one. So we had a 4. You can have other size rings. Obviously 6 is the most common because it's the lowest energy shape because of the angles of these bonds. But this direction, that direction would be the Diels-Alder reaction, and this direction is the reverse Diels-Alder reaction. And we can form, we can convert something with 2 double bonds in it and something with a single bond in it into a new molecule that has new bonds, that has more bonds, but it only has 1 double bond left. Effectively, we're taking this double bond, bringing it here. This one is going there, and this one is coming here. So these 2 new bonds used to be double bonds, and the other one is shifted. This is exactly the same as our other process. So now in the process that we've got here, we've got free radical growth of polymers, which can also go in the backwards direction. If we're growing polyethylene, then we're in a situation where we've got a lot of ethylene, a lot of monomer, and so the probability that a radical will hit another monomer is quite high. If we're in a solid polymer, in the ground or on the top of the ground, then the probability that a monomer, or that a radical inside the polymer finds a new piece of monomer is pretty much 0. the probability that it finds another polymer chain is way higher. So we've established that these radicals are very bad for polymers, and so we can think about how we're going to fix that. One of the things that we might do is give it some vitamin C, because we know that in humans vitamin C affects aging, and we would expect it to affect our polymer similarly. So this is our ascorbic acid, vitamin C, and we are going to oxidize it. We're going to steal one electron off it, which will go on to here. So this is our ascorbate, and we've made it into a radical by stealing an electron off it. That makes it a positive radical, and we can move this radical around our molecule in various ways to make it more stable. So it's a resonance stabilized state. That's good. That's why ascorbic acid, vitamin C, works as an antioxidizing agent, because it takes these oxygen radical species and it makes them into much more stable ascorbate radical species, which then hang around until they can find another radical and it breaks down the ascorbate, or it is regenerated. So we can take this and we can make a resonance form by breaking this bond and putting this in. That would give us a double bond here. Whoops. That would give us a double bond here, no double bond here, and a positive radical here, positive dot. Sorry about that, that's a bit messy. I've drawn it so often because I got it wrong that it's messy. So we can also take this bond and go in here. So we can also donate in from our, effectively deprotonate this and donate in from here. So that would form a double bond and it would move the radical out to this oxygen. But if we don't do that, that plus dot here, if we don't do that, we can also move this double bond into here as well, and the radical, that would move the radical up to here as well. So we've effectively got radical on here, radical on here, radical on here, and radical on here. We've got 4 centers where we can spread our radical over. And this one, not so easy to get it onto, but 4 atoms, that's much more spread out than usual. And the problem with radicals is that they typically are a very centered electron that has nothing to do, and so it tends to react. The problem with ascorbic acid, of course, is that it's got all of these polar groups on it, and so it doesn't dissolve in polymers at all, so we're going to have to think of something else. So much of polymer chemistry is controlling this reaction, the formation of the radicals at the beginning, or getting rid of them when they form. If we want to make these form faster, we can do one of 2 things. We could make more of this to start with, or make it form more easily, or we could make the rate determining step go faster. We could make the radical formation go faster. We'll start with the first one, because it's the first one. So we would like to make more of this, so we need to make more singlet oxygen. How do we make more singlet oxygen? Well, we have the problem. We've got our oxygen. Whoops. Let me draw that again properly. So this is our orbital diagram again. And what our goal is, if we want to make singlet oxygen, is to turn over one of these electrons. And we remember that it isn't possible quantum mechanically with just light, because it doesn't contain enough spin. It doesn't contain the thing that allows us to flip this spin. It contains energy, but the energy has to be associated with the right kind of momentum to be able to flip over the electron. So typically we can't do it. What we need is something that will absorb the light and turn over an electron, and usually that will be something like a dye with a heavy atom in it, although dyes without heavy atoms in work too, they just don't work as well. The rotation angular momentum comes from higher orbitals in the system, so the heavier the atom, the more funky orbitals it has, the more outside orbitals it has, they have more types of rotational angular momentum, and they can jump between energy states and flip over this electron. Typically we would use a dye that would dissolve in our polymer that can absorb ultraviolet light and then kick over this electron, so it would kick it up and then back down typically what would happen. If we do that, we can generate more singlets of oxygen. Just as with destroying a radical, to form a radical, we also need or could use something that can store an electron. So at the moment, we have a problem because we have to generate two radicals at once, and so that generates two things that are difficult to make at the same time. And it's not like our solvent is going to help, because our matrix, the material that we're in, is some kind of polymer, so it's not going to coordinate with it very well unless it's a very polar polymer. So typically, our matrix is going to resist this process. It's going to make it more difficult because it's a non-polar environment. It's behaving like a non-polar solvent. As my biomaterial students know from organic chemistry, if we go into a non-polar solvent, it's much harder to make things that are charged. Radicals aren't charged, but they behave like they're charged. They need some stabilization to be more likely. So one of the ways we can do this is we can make it make one at a time. So we would like to get rid of this OH dot effectively. Let's get rid of that. So what we would like is, instead of making the polymer radical and OH dot, we would like to make OH dot connected to something. So we need to be able to either donate an electron to make this into a bond, or to take an electron away. Ideally, to start with, we'd like to donate an electron so that we can form OH minus effectively. That's going to bond to whatever it is that's doing the work. One of the useful things for this would be a metal that can have oxidation states that are one apart from each other. Obviously, if it can have 2 and 4 and 6, that's not useful because that's all 2 electron transfers. But if it can have 1 and 2, or 2 and 3, or 3 and 4, we can use those, transition between those two oxidation states, to park an electron temporarily. So for this, we would want the lower oxidation state, and we can donate it to this, which would go up to the higher oxidation state, and then we can take it back off again to do the next one. Because we can either give an electron or take it away, and it helps. So because obviously we're going to get 2 electrons, we're going to get paired set of electrons each time, and that will remove one of the problems that we would have. So in this case, we're going to start with a simple case. We're going to start with iron. Why are we going to start with iron? Because this is a problem inside the body that you might already know about. So if we have iron, we can have iron 2. Iron 2 can donate an electron. So iron 2 plus OH dot goes to iron 3. Iron 3, and it will have an OH connected to it, an OH minus attached to it. And our charge is just a charge transfer, it's a transfer of 1 electron. When we want to take it back off again, we can take the H off something and make it into a water. That will get rid of our hydroxide, so we can go in the other direction. So why is this a problem inside the body? Well, our body contains iron, and it contains a couple, hemoglobin. I'm just waving my hand around because I'm imagining you can see my blood through there. It contains hemoglobin that switches from the iron 2 state to the iron 3 state. So we already have an active biological system that uses transfer from iron 2 to iron 3 in order to transport oxygen in its case. So iron is a problem because we've got a lot of it inside our body, and our body has to do something to prevent this switching happening and causing effectively short-circuiting metabolism. Because if during metabolism, one of the lower energy pathways will be to dump the energy some other way, and this will be one other way to do it because it can take 1 electron. The way that our body uses to do this is it contains some complexing agents, it contains some other organic compounds that sit around the iron, like this. Let's have it caged completely So they sit around the ion completely, and they force it into the ion 3 state, because to go into the ion 2 state would require us to take this hydroxide off. So if we connect our hydroxide in, if it's all one molecule, it makes it more difficult for the ion to be reduced. It changes its energy, it changes the energy of this transfer, and if we can shift it outside of what the oxygen would like to give, what the peroxide can give, then it will make it less catalyzing. An analogy would be the catalytic converter that we have for making margarine, actually, but for making a variety of things. We would like to make hydrogen more reactive, so we put a surface on there, and we can bond this hydrogen to the surface. And we can choose different metals to do this. If we choose some metals, this bond is as strong as the hydrogen-hydrogen bond, but that means that we've made it worse, because now we've got hydrogen attached to our surface. So we effectively, let's have our H. If we then do a reaction with it, we then form, let's have two, so we've got form 2 RH, so we form 2 new bonds, and we get energy out. That will be our typical reaction, and we want to catalyze this. If this has the same energy as this bond, then we've got twice as much energy that we have to break to get to the next stage, so the reaction actually goes down in speed. If this bond has a very low energy, then it won't form barely at all. So because we first of all have to break this, and so we will barely ever form any surface hydrogen. That's what happens on iron, for example. Hydrogen doesn't form this bond to iron very easily, because the bond between hydrogen and iron is not very strong, and therefore it tends to stay as hydrogen. Then we end up with pretty much no reaction either. The reactant, or the metal that we use, is typically platinum, and by chance, obviously chosen, people have selected metals over a long period to get the best ones. Platinum is one of the best ones, because this bond is almost exactly half the strength of this one. So it forms, but we don't waste too much energy in binding it to the surface. Obviously, there are practical speed constraints, so the stronger these bonds are, the faster we can get the hydrogen onto our surface, and the weaker the bonds are, the easier it is to get it to react. So it depends on how easy it is to get this to react, whatever we had to make that, and it depends on how much hydrogen we can pump into our system. So in an industrial system, it depends on the temperature and all kinds of pressure and all kinds of things. In our body, obviously, we have the same problem. Our body has to regulate concentration of hundreds and hundreds of things all at the same time, but also energy. If we shift the ion 2 to ion 3 couple, the ion 2 to ion 3 reaction, to a different energy, then there are some things that it can't react with, because it just doesn't make it more effective. So the catalysis doesn't occur. Obviously it can react with it, but it's not going to make it any faster than it was doing nothing, and that's good. What we don't want to do, what our body doesn't want to do, is make a bad reaction more likely. So we're back to the same problem. How do we get something to dissolve into a polymer? You may be familiar with this. So we've got some iron, and a typical way to do this would be to form a soap. What do we know about iron? We know iron is a reasonably hard metal. What do I mean by hard? To those of you not from not from biomaterials, what I mean by hard is the orbitals on it that are going to interact with, ooh, that's a funny shape. The orbitals on it that are going to react with our ligands, whatever was going to stick to it, are quite small. That is bad, because it means it's hard for the ion to dissolve into the polymer. If we have small orbitals, it means the electrons are in here very tightly held. It's an ion 2+ or 3+, so there aren't any electrons in there, but that's where we're going to put them. We need to put them in there from something. We can put them in there from oxygen, we can put them in there from sulfur, we can put them in there from chlorine, we can put them in there from bromide. but the strength of the bond is dependent on the overlap. So if we have something that is similar size and similar angle, let's have it like that, similar size and similar angle here, then we can attach to it better. If we have something that's much bigger, then the overlap, the energy that we gain from it is much lower. Because iron is comparatively hard, that means small, so it's a low, it's high up on the periodic table effectively, it's near the beginning, because the periodic table is weirdly upside down. So iron is close to the beginning of the periodic table, so its orbitals are comparatively small compared to metals down near the bottom. Then we will tend to interact with oxygen. So if we interact with oxygen here, we can imagine a typical oxygen ligand would be acid. So an acid would look like this, and it has a negative charge. Oops, that was bad. It has a negative charge between the two, and it has some kind of chain going off into the distance. And if we had iron, we would form an octahedral complex with it, so we would need several of these ligands. We'd need several acid groups. This is the same as the scum in your sink. So this would be a typical soap. I forgot to count how many of them there are. I think there are 12, so that would make it SDS. Make it not SDS, but it would make it dodecanoate. And this is the sodium ion. I forgot to put the plus on there. So we've got a soap. This would be a normal soap that you might find in your bathroom, and that is soluble in water. If we bring that along and we mix it with tap water, it will typically contain some calcium ions, and calcium ions are 2+, and they also typically bind very well to these soap molecules. They have a similar size. They're actually slightly better at interacting than the sodium was. And if we have another soap, we can connect it to 2. Now we've got 2 soap molecules around our calcium, and this is completely insoluble in water because the charge is all associated in the middle, and we've got all of this long chain on both sides. Those interact with each other, hydrophobic interactions, and we end up with a thing that we call soap scum. It's the grey, horrible stuff that builds up around your sink, particularly here, actually. If we deliberately make that pure with iron or cobalt, we can make a catalyst that will catalyze the radical formation in our polymers, and that will make the degradation of the polymer faster than it would be otherwise, because we're hitting the rate determining step. If we use a catalyst, if we use a photocatalyst to make more singlet oxygen, then we will make more peroxide to start with, and that will obviously also linearly increase the rate of reaction, because if we've got twice as much peroxide, then the probability of one of them breaking is obviously twice as high. So there are 2 critical things that I'm interested in here. One of them is that it's fairly normal inside polymers to vary the rate of reaction with oxygen. So a typical polythene bag of typical polymer that we would carry around with us would contain some kind of antioxidants to slow the reaction down, and they would have been affected in exactly the same way as our iron soap or our cobalt soap. So they would also have chains of non-polar material, non-polar chains grafted onto them, so that they will be soluble in the polymer. They will be added relatively late, otherwise they're going to react with oxygen, and they will be mixed in with our polymer and effectively determine its lifetime. When we take that polymer and go and recycle it, then effectively what they're going to do is they're going to chuck in some more so that it removes some of the radicals that are floating around, reprocess it, and make some more. But if we take some oxo-degradable polymer, we're going to make it difficult. That's the problem, the ethical and conceptual problem with these. Obviously, they are great materials, but there is a problem. If we mix them in with our normal waste, then we're going to be mixing in catalysts into our recycled material. We can throw in extra antioxidant in there and that will make it usable, but it will reduce the amount of times that we can recycle it. On the other hand, if we have completely biodegradable polymer and we mix it in with our polymer, it doesn't mix very well and then we have to throw it all away. So we have two problems with our alternative biodegradable materials. These oxo-degradable materials are supposed to be the better one from that purpose, from the purpose of a normal recycling system is more tolerant to a small amount of oxo-degradable polymer than it is to a small amount of biodegradable polymer, because it will mix in, it behave completely like a normal conventional polymer. We don't need any new process for it. We don't need to extract it. We don't need to do anything else. So it has interesting interactions with recycling. And as you may know from recycling would be the ideal solution if we could do it, because then nothing goes into the environment. We don't actually need any new resources apart from whatever we need to reprocess it. That is obviously not feasible, but these other alternative materials have their own new problems and challenges that we can deal with better or worse. The other thing that I would like you to start to think about is that all of the breakdown products of these are still fairly complicated molecules. So what we were making was a ketone and an alkene. So that was what we end up when we managed to break a double bond. We end up single bond, sorry. So when we managed to break the carbon-carbon chain, we're effectively generating a ketone, possibly an OH moiety. So we're going to end up with something with oxygen in it. That's good. That looks biodegradable eventually. This is biodegradable eventually, but it's going to take several steps, and these intermediate molecules might be worse than the starting material, because the starting material was just polyethylene. It doesn't matter whether polyethylene is toxic or not. It's completely insoluble, so it can't do anything. It can't get into your body. It can as particles, but it can't get into your body as a molecule. It doesn't interact in the same way that small molecules do. These small molecules are new small molecules that biology now has to deal with. So we end up with an intermediate set, and obviously these are going to fall through the question of is it biodegradable or not, because we had one of the definitions being it passes through a certain sieve size after a certain time. If we make it brittle and break it into tiny pieces, then we haven't done much. We've actually made bigger molecules, but we can get through a sieve. If we make it into small molecules that are not particularly friendly to biology, they will also go through a sieve. So we haven't really proved that it's biodegradable. It will be, but we've got an intermediate step that is questionable at least. Okay, we'll come back to some new subjects next time.